Hi, I'm Libby Kirk, and my presentation topic is on the behaviour of large phyllosilicate-rich strike-slip fault zones, focusing on the Carboneras fault. So what is a strike-slip fault zone? Well, Fawson defines strike-slip faults as where the displacement vector is parallel to the strike of the fault and thus parallel to the surface of the Earth. Strike-slip faults can be sinistral, displacement to the left, or dextral, displacement to the right. For a strike-slip fault, the focal mechanism shown will indicate whether the fault is right or left lateral with motion towards the black compressional quadrant. On the left, it will be a left lateral fault, because if you stood at the fault plane facing the other side, in order to find the offset feature, you would have to move to the left. The opposite is true for a right lateral fault. The Carboneras fault zone is a major sinistral strike-slip fault located on the Iberian Peninsula in the province of Almeria, southern Spain, forming as a result of tectonic movement between the Eurasia plate and the African plate. It has a northeast-southwest trend and forms part of the Eastern Betic Shear Zone, extending for about 50 kilometers onshore and continuing offshore into the Alboran Sea for at least a further 90 kilometers. The fault is believed to have 40 kilometers of offset, cutting through the entire crust and lithosphere, and is still considered to be seismically active, hence why it is considered a large fault zone. The fault initiated in the Middle Miocene around 18 million years ago. Movement continued on the fault until around 5 million years ago, yielding long-term average slip rates of around 2.7 millimeters per year. So what is so special about this large fault zone? Well, the Carboneras fault differs from other large displacement strike-slip faults because it contains a high percentage of phyllosilicate-rich materials. This feature affects the mechanical properties, which in turn determines the internal structure of the fault. Its unique internal structure is why the Carboneras fault zone will be discussed in this presentation. First, a brief geological background of the area will be discussed before diving into the deformation mechanisms within the Carboneras fault. The fault zone incorporates many different rock types of the region. The basement rocks in the region consist of andalusite and garnet-bearing mica schists, phylites, and dolomites. These deposits are followed by sequences of marls, turbidites, gypsums, and reef limestones, and eventually topped off with volcanoclastic sediments and calc-alkaline lava flows. It is important to note that igneous rocks contained within the fault zone show intrusive relationships with very little deformation, so are not of significance here. The fault gouge exposure consists of mica schists and phyllosilicate-rich clay-bearing rocks. The typical mineralogical assemblage in these gouges include muscovite, illite, chlorite, quartz, with minor amounts of gypsum, albite, and graphite. The layers of the fault gouge are typically on the order of several meters wide. So what exactly are phyllosilicate minerals, and how do they affect deformation in the Carboneras fault? A phyllosilicate is any silicate mineral that comprises tetrahedral structures that are linked to form sheets. Examples are shown in the table. They are introduced to fault zones through mechanical incorporation and/or mineral changes during diogenic and metamorphic reactions. Because phyllosilicates are hydrated structures, they have a significant effect on the hydration of fault zone. This in turn has a large consequence on the frictional behaviour of fault zones and mechanical factors such as fault strength. During deformation caused by shearing during fault movement, the phyllosilicate minerals within the fault gouge transition from the elastic into the plastic regime. Here, strain hardening can occur. Fawson states strain hardening occurs when the stress necessary to deform the rock must be increased for strain to accumulate because the rock becomes stronger and harder to deform. Strain hardening is interpreted to be due primarily to mutual misalignment of mica flakes, which contributes to progressive porosity reduction and formation of oblique shear features during shearing. Strain hardening produced the even distribution of strain within the individual fault gouge layers and resulted in fault creep being the most dominant mode of failure along the Carboneras fault. Furthermore, deformation within a phyllosilicate porous material is different to that in non-porous materials. Pore space gives the grains a unique opportunity to reorganize. If the grain is weakly cemented together, then the grains will reorganize by rotation and frictional grain boundary sliding during deformation. In other cases, grains can also break internally. However, in either case, the deformation is likely to localize into narrow zones or bands to form structures known as deformation bands, and this is visible within the Carboneras fault zone. Finally, phyllosilicate minerals are highly permeable and will affect fluid transport within the fault. The fault structure can store fluids in the low permeability gouge or within the higher porosity lenses contained by the gouge. If pressurized fluids are key controls on the strength of large faults, then the nucleation of slip events may either occur in the fault gouge or within the fractured protolith lenses in the damage zone. The internal structure of the Carboneras fault zone does not fit with the previous conceptual module for large strike-slip fault zones, shown in Image A. This is because of the phyllosilicate-rich fault gouge strands that show wide distributed deformation and the large fractured blocks of dolomite which show highly localized deformation that is bounded by the bands of phyllosilicate-rich material in the damage zone. The difference is because dolomite, in contrast to phyllosilicate gouge, is made of calcium-magnesium carbonate and exhibits strain weakening and fracturing from brittle deformation during shearing. This contrast in rock strength between these two different rock types makes up the Carboneras fault zone and is shown in Image B. The images on the screen show the internal structure of the fault gouge in the Carboneras fault zone. The gouge is highly foliated, showing typical brittle fault rock fabrics. These include a primary P foliation defined by aligned phyllosilicates in a plane oblique to the shear direction, and radial shears parallel to the shear direction, which cross-cut and locally reorient the P foliation. There's also quartz vein clasts, which become intensely fragmented by the movement on the fault and often have asymmetric tails that clearly indicate the shear sense. Slicking lines found within the dolomite layer from the damage zone of the Carboneras fault represent shear fracture surfaces in rocks that are polished, linear grooves formed by mechanical abrasion. Finally, the orientation of the structural features from both the fault gouge and dolomite layer can be plotted on a lower hemisphere projection as shown on screen to determine the sense of slip. Image A shows the P foliation and the R1 shear data from the fault gouge. B also shows the P foliation and the R1 radial shear data for another locality along the fault gouge, showing much less variability than A. And C shows the orientation of localized fault planes and associated slicking lines developed within the dolomite blocks intruded within the fault zone. Lastly, D shows an idealized sketch showing the predominant foliations developed within the fault gouge layers. In general, the fault slip data indicates that the movement recorded was almost exclusively left lateral strike slip, as previously stated. Overall, the internal structure and mechanics of large strike slip faults is controlled by the composition of the rocks within the fault zone. Phyllosilicate-rich fault zones, such as the Carboneras fault, differ from normal strike slip faults by the means in which they deform. Strain hardening, frictional sliding, and grain rotation are the main deformation mechanisms within the Carboneras fault gouge, resulting in fault creep being the most dominant mode of failure along the fault, with this being in direct contrast to the strain weakening in the interbedded dolomite rock. Finally, structural features produced during shearing tell us the orientation of the strike slip fault and indicate a left lateral strike slip.